Good evening, and welcome back to SleepWise. Tonight, we begin with an element that has lived two very different lives in human hands, and will hold both of them gently, the way you might hold a warm cup in the dark. In one life, uranium becomes a steady, almost ordinary kind of comfort, turning heat into steam, steam into motion, and motion into light that waits for you at the end of a hallway. In another life, that same hidden heat is released far too quickly, and history learns in a single bright instant that some forms of power cannot be taken back. We won't linger on fear tonight. We'll linger on understanding, because understanding has a calming quality of its own, like learning the name of a wind you've felt for years. If you listen closely, the strange truth is that uranium is not powerful because it is loud. It is powerful because the energy it carries is packed deep inside the nucleus of an atom, in bonds so tight and ancient they were forged long before Earth had seas, long before there were lungs to breathe or eyes to close. Most of the world's familiar fires live in the outer edges of atoms, in the gentle trading of electrons in chemical handshakes that release warmth by rearranging what is already near the surface. Uranium's story lives deeper than that, where a tiny change can release a great deal of heat, and where the difference between usefulness and catastrophe is not magic, but tempo. Slow, guided, and watched over, the energy becomes a patient glow. Fast, rushed, and uncontained, it becomes a storm. And so, this is a story about pacing, about restraint, about what it means to learn something true about nature and then decide how to live alongside it. For now, let your shoulders soften. Let the room dim around you as if the night is turning down a careful dial. In the segments ahead, we'll drift backward into deep time, into starlight and stone, into the quiet geology that hid uranium in the crust for ages, and into the calm science that eventually taught us how to measure its faint, invisible signals. We'll visit the rise of nuclear energy as a disciplined craft of control, and we'll acknowledge, without spectacle, how the same discoveries were also pulled into the darkest urgency of the 20th century. Then we'll return again and again to the idea that the gentlest part of this story is not the atom itself. It is the human choice to slow down, to build layers of care, and to treat the most powerful things with patience. Take a slow breath in. If you can, notice the quiet hum of modern life somewhere far away, the grid and its invisible currents, and let that distance make everything feel softer. And as you breathe out, imagine the earth beneath you, quiet and immense, holding its minerals the way the night holds silence, without hurry, without judgment, simply waiting. Tonight, we stay close to that word you felt a moment ago, tempo, because uranium's great difference is not that it breaks the rules of nature, but that it reveals a deeper rule, one written in the nucleus, where energy can be stored more densely than in any flame. In ordinary fire, atoms trade electrons like quiet coins, making and breaking chemical bonds, releasing warmth in small familiar portions. Those portions add up, of course, but each bond is a surface-level arrangement, a gentle reshuffling at the edges of matter. Nuclear energy begins where chemistry cannot reach, in the tight embrace between protons and neutrons, held together by the strong nuclear force. It's a force that works only across tiny distances, but within that tiny space it is immense, like a powerful clasp you can't quite see. In nature, some nuclei sit in especially restful arrangements, and mid-weight elements are, in a sense, more comfortably bound than the very heavy ones. So, when a heavy nucleus divides into two medium ones, the ending can be calmer than the beginning, and the difference is released as energy. A small amount of mass becomes heat, and the universe keeps its account perfectly through the simple relation E equals mc squared. It sounds like a slogan, but it is really a lullaby of consistency, a promise that nothing is lost, only transformed. In uranium, the transformation often arrives through fission, when a heavy nucleus splits into two lighter nuclei, and the pieces fly apart with kinetic energy that quickly becomes heat. Along with that heat, a few neutrons slip free, and those wandering neutrons are what make the story feel alive. If one of them finds another suitable nucleus, it can prompt another split, and another, like a line of dominoes that can be slowed, stopped, or allowed to continue. And here is where the human role returns, not as drama, but as design. In a reactor, the goal is never speed for its own sake, but steadiness, a controlled chain reaction that behaves more like breathing than like lightning. Engineers use materials that slow neutrons down, and other materials that quietly absorb them, and cooling systems that carry away heat the way a river carries away summer warmth. The details can be complex, but the guiding idea is simple. Keep the rhythm calm. Keep the reaction predictable. Keep the heat useful. Tonight, we are not building anything. We're only learning the shape of the story, so it can feel less sharp, more understandable, like a coastline seen from far above. One more quiet detail matters, and we'll return to it later. In natural uranium, only a small portion is the variety that most readily sustains this rhythm. That is why enrichment exists, and why it asks for patience. And now, with that gentle physics resting in the background, we can drift backward toward the places uranium waited, long before it ever met a human name. And so we travel, not by miles, but by time. Imagine the earth beneath you as a library of layered pages, each stratum a quiet record of heat, pressure, and water, moving patiently through stone. Uranium is not sprinkled evenly like salt. It gathers where geology gives it a reason to gather, and those reasons are slow, methodical, almost tender. Long ago, as continents assembled and broke apart, molten rock cooled into granites and other crystalline bodies, and uranium, being a heavy element, often found itself tucked into certain minerals especially dark, dense ones like uraninite. In some places, it sits in hard crystalline rock, and in others, it settles into old sedimentary layers, sands and gravels that once lay under rivers or shallow seas. Then water arrived, not as a single river, but as a long procession of rain and groundwater seeping through cracks, dissolving tiny amounts, carrying them onward. Over ages, chemistry and flow can concentrate what was once faintly dispersed, the way repeated tides can leave a line of shells higher on a beach. Some deposits form when oxygen-rich water moves uranium in solution, and then conditions change. Less oxygen, different minerals, different chemistry, and uranium settles out again, precipitating as new solids. Other deposits sit near great boundaries in the crust, where older rocks meet younger layers, and fluids circulate along those edges like slow conversations between eras. It can be surprisingly ordinary in its mechanics: water, time, and a few changes in the underground environment. But the scale is anything but ordinary. We are talking about processes that take longer than civilizations, longer than languages, longer than any single story a person can tell. This is part of why uranium feels like deep time made tangible. It asks you to think in millions of years, and then to soften that thought until it feels almost peaceful. Even the word ore is simply a human label for a place where the concentration became high enough to notice, high enough to mine. Before that moment of noticing, uranium is just another guest in the crust, quietly present, quietly changing, emitting faint signals that drift through rock and fade away. Much later, people would learn to listen for those signals with instruments, turning invisible whispers into maps and drill sites. And while it waited, the planet kept making landscapes. Mountains rose, wore down, and rose again, and rivers redrew their paths, and deserts bloomed and vanished, and the elements stayed, patient and unmoved by the hurry of weather. In the next breath of our journey, we'll lift our eyes from stone to starlight, because even this heavy element began as something weightless, atoms scattered in space, before they ever settled into Earth. Far above those layers of rock, the story begins in a place with no ground at all. Before Earth had continents, before it had oceans, there were only clouds of gas and dust, slowly gathering, slowly cooling under gravity's quiet insistence. Light elements like hydrogen and helium were born first in the earliest moments of the universe, simple and abundant. Heavier elements are different. They are not made gently. They are made where nature briefly becomes extreme. Inside stars, over long lifetimes, lighter atoms fuse into heavier ones, releasing heat and light that warms surrounding space. But uranium is heavier than what most stars can comfortably create in their ordinary burning. To reach uranium, the universe needs a rarer kind of workshop, one where neutrons arrive in great numbers, fast enough that nuclei can absorb them before they have time to settle. Astronomers call this a rapid process, and you can picture it as a storm of tiny particles, a brief, intense moment when matter is pushed into heavier and heavier forms. Such moments can occur in the violent endings of massive stars and in the collisions of dense stellar remnants, events so energetic they can send ripples through space itself. Out of that violence comes something strangely peaceful, a new inventory of elements, scattered into the dark, mixed into future clouds, destined for future worlds. Uranium, then, is not just an earthly substance. It is a souvenir from an older cosmos, carried into our planet as it formed from dust and debris orbiting a young sun. When Earth melted and separated into layers, much of the heavy material sank toward the interior, and some remained in the crust, bound into minerals that could survive cooling. And all the while, uranium was already doing its quiet work. Radioactive decay began the moment those atoms existed, a slow ticking that never needed an audience. Often it happens in steps, as uranium becomes other elements, releasing tiny particles along the way like soft, invisible notes. Some of those particles are helium nuclei, what scientists call alpha particles, and over immense spans of time they can leave behind helium trapped in rocks, while the uranium slowly walks its way toward stable lid. That gentle rearranging releases heat inside stone, contributing, along with other isotopes, to the warmth that helps keep Earth's interior active. It is a calm irony. An element associated with modern machines has been warming the planet from within for billions of years. Tonight, let that thought feel soothing. A great power already at work in silence long before we learned how to name it. And as we drift back down toward the surface, we'll follow how those cosmic atoms became earthly ores, and how the first human eyes began to notice their unusual color and weight. When you return from starlight to Earth, the element feels less like a concept and more like a material, something that can stain a fingertip or hide in a rock that looks ordinary until light catches it. Uranium minerals are often dark and heavy, sometimes glossy, sometimes dull, and in certain forms they can show surprising yellows and greens. Long before anyone spoke of nuclei, people noticed those colors. In parts of glass making and ceramics, small amounts of uranium compounds were used to tint glazes and glass, creating a pale green that can glow under ultraviolet light, like moonlit water. It wasn't a prophecy. It was simply craft, a human love of color meeting a mineral that happened to behave strangely. The scientific story begins in the age when chemistry was learning to be precise. In the late 18th century, researchers were cataloging minerals, heating them, dissolving them, weighing what remained, trying to understand what was truly new and what was only a mixture. A dark ore called pitchblende became one of those puzzles. From it, a German chemist, Martin Heinrich Klaproth, identified what he believed was a new element and named it uranium, after the planet Uranus. which had been discovered only a few years earlier. Even the naming feels like a quiet sign of the era. New worlds in the sky, new elements in the lab, the sense that nature's catalog was larger than anyone had imagined. Later, other chemists would isolate uranium metal itself, dense and silvery, a material with a gravity you can almost feel in your palm. For a time, though, uranium was mostly a curiosity with practical edges. Pigments for tiles, glazes for pottery, industrial colors that brightened ordinary objects. No one knew yet that it was gently emitting energy all the while. It was like owning a lantern and thinking it is only a beautiful object, unaware that it also has a hidden flame. And out beyond the laboratories, minds did what minds have always done. Men and machines following seams of usefulness, bringing dark stone into daylight, not yet aware of the invisible story in the dust. That hidden flame would be noticed in the 19th century, when careful experiments began revealing rays and emissions that didn't fit any ordinary chemical explanation. But we don't need to rush there. Tonight, it's enough to feel how slowly understanding arrives, how long an element can sit in plain sight before its deeper nature is recognized. As the world grows quieter around you, imagine the early laboratories, glassware, scales, powders ground patiently, notes written in neat lines, the steady confidence of people who believed the universe could be measured. In the next segment, we'll follow the moment when invisible energy became undeniable and uranium stepped from colored mineral into the heart of modern physics. Tonight, we arrive at a turning point, not with fanfare, but with a covered photographic plate. In the late 19th century, the world was learning new ways to see, and photography had become a quiet witness. Henry Becquerel was studying minerals that glowed after exposure to light, and he placed uranium salts near a photographic plate wrapped in dark paper. He expected sunlight to matter, so when cloudy weather arrived, the experiment waited in a drawer, tucked away with no urgency. Later, when he developed the plate, an image appeared anyway, as if light had reached through the wrapping and touched the surface. The uranium had marked the plate in darkness, steadily, without heat, without flame, without any external spark. It was a gentle clue that something was leaving the material itself. Around the same time, scientists were already startled by other invisible rays like X-rays that could pass through flesh and shadow bone. But uranium's lesson was quieter and more intimate. No machine was needed, no electrical coil, no dramatic apparatus. The source was inside the substance, as if the stone carried a faint lantern of its own. Marie and Pierre Curie took the question and treated it like a long walk that could not be rushed. They measured the activity of uranium ores and noticed that some samples were far more active than uranium alone could explain. From that mismatch came months, then years, of dissolving and crystallizing pitchblende, separating fractions again and again, repeating the same careful steps until patterns emerged. They found new substances with intense activity, later named polonium and radium, and they helped give the phenomenon a name that could be shared. Radioactivity, a word that can sound sharp, but really means something simple tonight. Certain atoms change from within, and in changing, they release small pieces of matter or pulses of energy. The atom, once imagined as a hard bead, began to feel like a small system with an interior life. And that idea, surprisingly, can be calming, because even the invisible follows rules. Even deep inside a mineral, there can be a rhythm, steady enough to measure, steady enough to map, steady enough to understand. Let that rhythm settle in your mind as you breathe out. A stone in a drawer, a wrapped plate, and the quiet discovery that the night can leave fingerprints. And once the fingerprint was there, scientists did what they always do. They leaned closer, not with panic, but with instruments, notebooks, and the steady patience of people who believe that mystery can become clarity. Tonight, we stay with the new word radioactivity, and we let it become gentle. Radioactivity is not a personality, not a mood of nature, but a process, an atom adjusting itself toward a calmer arrangement. Some nuclei are stable and remain as they are, like mountains that hold their shape across seasons. Other nuclei are a little too heavy or a little imbalanced, and over time they move step by step toward stability. They do it by releasing something. One common release is an alpha particle, which is a tight bundle of 2 protons and 2 neutrons. It is heavy. It does not travel far in air, and a sheet of paper can stop it, which is why context matters whenever we talk about radiation. Another kind is beta radiation, where a nucleus reshapes itself by converting a neutron to a proton, or a proton to a neutron, and a fast-moving electron or its counterpart slips away. Beta particles travel farther than alpha particles, but they still yield to thicker materials, like fabric yielding to a closed door. Then there is gamma radiation. Gamma is not a particle with mass, but a pulse of energy, a photon released when a nucleus settles down from an excited state. It can pass through more materials than alpha or beta, which is why shielding can require dense substances and careful design. Still, even gamma is not a monster. It is a form of light, simply far beyond what our eyes can see. What makes these emissions measurable is that they can ionize matter. They can knock electrons loose, leaving tiny trails of charge in air, in plastic, in metal, and sometimes in living tissue. That charge can be collected and counted, turning invisibility into a signal, like footsteps made visible in fresh snow. Uranium, in particular, does not become stable in a single step. It changes through a long family line, a sequence of decays that produce other elements along the way. Over deep time, those steps drift toward stable lead, like a long river, eventually reaching the sea. Along the chain, some descendants are gases like radon that can seep slowly through soil and rock, a faint reminder that the earth has a quiet breath. This is also why the planet carries a natural background level of radiation. Granite, certain sands, high-altitude air, and even some foods contain trace radioactivity, small enough to be part of ordinary life. None of this asks for fear. It asks for scale and for care and for the simple truth that dose matters, the way volume matters in a room. Tonight, let the world feel well scaled again. A whisper is not a shout, and understanding is one of the softest forms of shelter. And as we keep drifting, we'll meet the most soothing idea in this subject. The idea that even randomness can have a dependable rhythm. Half-life sounds like a technical term, but it behaves like a lullaby. It is the science of predictable fading, the calm mathematics of change that keeps its pace no matter who is watching. Imagine a very large crowd gathered quietly in a room. Each moment, a few people stand and leave, not because they were chosen, but because that is simply how crowds thin over time. No one can say which person will leave next. But with a large enough crowd, you can say something steady about the group. A half-life is the time it takes for half of a collection of unstable atoms to transform into something else. Not to disappear, not to be destroyed. To change, to become a different nucleus, a different element in the long family line. Then half of what remains will transform again, and half again, step after step, like a candle that always dims by the same rule. For uranium, some half-lives are so long they stretch beyond human imagination. That is why uranium still exists in nature after billions of years. Its change is not hurried. It is a slow drift through descendants, each step releasing a little energy, each step leaving a slightly different atom behind. Half-life also carries a quiet lesson about uncertainty. Each atom's moment is unpredictable, like the exact instant a leaf will fall. Yet the forest follows a season, and the whole orchard knows when autumn is near. Because half-lives are steady, they become clocks embedded in rock. By comparing how much parent isotope remains to how much daughter product has accumulated, geologists estimate the age of minerals and meteorites. Time leaves a faint ledger inside crystals, and careful measurement can read it, even when no written record exists. Uranium even offers more than one clock, because different uranium isotopes keep different tempos. One lingers for billions of years. Another changes faster, still slow by human standards, but quick enough to matter for how uranium behaves in reactors. These differences are invisible to chemistry. They matter in the nucleus, where small changes in mass become meaningful differences in behavior. Tonight, that might be the most soothing thought. Even very powerful processes can be patient. Even change can have a rhythm you can trust. And in the next segment, we'll see how humans learn to listen for that rhythm, turning the invisible into something countable and calm. Sometimes The slow decay of uranium and its relatives is part of what warms the earth from within, a faint internal hearth that helps keep the planet restless in the gentlest way. So, when you hear half-life, you can hear slow warmth and let it feel like a steady background, not an urgent signal. And because the rhythm is so dependable, it invites a kind of trust. You don't have to predict the next atom, only the steady shape of time. To understand anything invisible, humans learn to build ears. Radioactivity is not something you can reliably sense with your skin or your eyes. So the first step toward calm was measurement. Early instruments noticed how radiation could ionize air, turning it slightly conductive, as if the atmosphere briefly remembered a path. An electroscope could show this. When charged, its thin metal leaves repel one another and stay apart. But ionized air lets the charge leak away, and the leaves slowly fall closer together. It is a small motion, almost like a plant relaxing at dusk, and it tells you that something unseen has passed through. Later came detectors that could count. A Geiger-Müller tube at a high level is a chamber that registers ionizing events as tiny electrical pulses. Each pulse becomes a click, a sound that can feel oddly calming once you realize it is not chaos. It is evidence arriving one tap at a time. Other detectors use light. A scintillator is a material that gives off a faint flash when radiation deposits energy in it, and those flashes can be amplified and counted. Then there were instruments that made the invisible briefly visible. A cloud chamber fills a space with supersaturated vapor, and when charged particles pass through, they leave thin tracks of droplets, lines drawn in mist. These tools change the emotional tone of the subject. When something can be detected and quantified, it becomes less like a rumor and more like weather. You can map it, plan for it, and build boundaries around it. Measurement also became a lantern for geology. Prospectors could walk a landscape and hear the clicks rise and fall like a shoreline changing underfoot, hinting where heavy elements gathered. And as the science matured, so did the quiet language of safety. Distance matters because intensity spreads out like light from a candle. Time matters because exposure is also duration, like sound in a room. Shielding matters because different materials are better at slowing or absorbing different emissions. These are simple levers, gently applied. Step back, shorten time, add a barrier, and let the world feel manageable again. Even the units scientists use are, in their own way, a form of reassurance. They are reminders that what can be measured can be managed, and what can be managed can be approached with calm. In modern places that work with radiation, monitors are always listening, like quiet smoke detectors for an invisible kind of weather. Their presence is meant to replace guesswork with calm facts, so that attention can stay soft and steady. There are checklists, training, and routines designed to make the extraordinary feel ordinary. In that way, safety becomes a habit, and habits are what let the mind rest. Now we return to the nucleus, where uranium keeps its deepest secret. To picture it, imagine a crowded room held together by a strong, short-range kindness. Protons all carry the same positive charge, so they would prefer to push apart, and yet they remain bound because the strong nuclear force acts like a powerful clasp at very short distances. In light elements, this balance is relatively simple. In very heavy elements like uranium, the crowd becomes harder to hold. There are many protons pressing outward, and the nucleus must constantly balance attraction and repulsion, stability and strain. Physicists speak of binding energy, the energy required to pull a nucleus apart. They also notice something quietly elegant. Mid-sized nuclei tend to be bound more tightly per particle than the heaviest nuclei. So, a heavy nucleus can sometimes reach a calmer state by becoming two smaller ones. When that happens, the final pieces are, in a sense, more comfortably bound. The difference is released as energy. A tiny sliver of mass becomes heat. And because the conversion from mass to energy is so large, the heat is immense compared with chemical fires. Most of it appears as the motion of the fission fragments, which quickly becomes warmth in the surrounding material. And often, a few neutrons are released as well, like quiet messengers leaving the scene. Those neutrons matter because they can sometimes encourage other nuclei to split. This is the seed of a chain reaction, a multiplication that can be guided or stopped, depending on the environment. Here, uranium becomes a story of isotopes. Isotopes are atoms that are chemically the same, but differ slightly in mass because they contain different numbers of neutrons. They make the same compounds and look identical to chemistry. Yet, in the nucleus, that small difference changes how readily they fission and how likely they are to keep a chain reaction steady. In natural uranium, only a small fraction is the isotope that most easily sustains a reactor's gentle rhythm with slow neutrons. That is why enrichment exists. Enrichment is the tightly controlled process of increasing that fraction. And it is difficult not because of mystery, but because the isotopes behave almost identically. You are trying to separate atoms with the same chemistry, nearly the same size, and only a slight difference in mass. So the separation must be done in many small, patient steps, repeated again and again, like sifting fine sand through ever finer screens. It requires precision and strict oversight, because the same capability that serves civilian fuel cycles must be handled with restraint. Tonight, we don't need the machinery, only the feeling of the challenge. And in the next segment, we'll carry that understanding into the calm architecture of reactors, where tempo becomes design, and design becomes steady light. Tonight, we let the idea of a chain reaction become calm. A chain reaction is not by itself a threat or a promise. It is simply a pattern, where one event can make the next event more likely. In uranium, the pattern begins when a nucleus splits and a few neutrons slip free, small messengers released into the surrounding material. If those neutrons are absorbed, the story ends quietly, like a spark that lands on stone. If they are slowed and guided, they can be invited to cause another fission and then another in a steady rhythm that can be measured in heat. The word critical appears here in textbooks, but tonight we can translate it into something softer. It means balance. Not too many neutrons escaping, not too many being absorbed, just enough continuing that the pace stays even, like a candle flame that holds its shape. In a power reactor, the whole art is to keep that balance gentle. Neutrons can move too fast to be useful in certain designs, so materials called moderators help slow them, letting them linger, making them more likely to be captured in the right way. Other materials act as absorbers, quietly taking neutrons out of circulation, like soft curtains that calm and echo. And then there is heat, the main product we actually want. Heat must be carried away continuously, because removing heat is another way of keeping the tempo steady, preventing the reaction from drifting into uncomfortable territory. So the chain reaction, in its peaceful form, is not a runaway. It is a steady conversation between physics and engineering, a feedback loop where changes in temperature, neutron behavior, and material properties push the system back toward calm. Even the word reactor can sound tense, but you can picture it as a carefully designed hearth. A hearth is not meant to roar. It is meant to warm, and like any good hearth, it needs airflow, boundaries, and someone attentive enough to adjust the draft. Tonight, notice how often the same principle returns. The nucleus holds tremendous energy, yes, but the story is really about rate and about the human decision to slow things down. Because energy released across months becomes electricity you can live beside, energy released in moments becomes something else entirely, and we do not need that path tonight. So, we stay with the slow path, we stay with the warm path, and we let the idea of balance settle into the body, like a steady pulse you can trust. You might even imagine the neutrons as tiny travelers in a dark hallway. The walls, the doors, and the soft carpets are the materials we choose, and with those choices we decide whether the travelers rush, wander, or come gently to rest. So when you hear that uranium is powerful, you can translate it into a calmer phrase. It means the nucleus offers a great warmth, and the task is to let that warmth arrive slowly enough to live beside. Now we return to the quiet problem that sits between stone and reactor fuel. Natural uranium is mostly one isotope, and only a small fraction is the isotope that more readily supports certain kinds of sustained reactions with slow neutrons. That small fraction is enough for the Earth to have carried uranium for billions of years, but it is not always enough for the fuel designs humans built. So a separate chapter appears, one that sounds technical, yet is mostly a story of patience. Enrichment. At a high level, enrichment means increasing the share of the lighter uranium isotope compared with the heavier one. And what makes it difficult is almost soothing in its simplicity. Chemically, the isotopes are nearly indistinguishable. They make the same compounds. They bond the same way. They look identical to chemistry, like two keys cut to the same shape. The difference is subtle mass, a few extra neutrons, and that difference is too small for ordinary chemical separation. So, enrichment relies on physical methods that take advantage of that tiny mass difference. And they do it in many small steps, not one dramatic separation, but a long sequence of slight nudges, repeated, like filtering a river through 1,000 gentle bends, each bend changing the flow only a little. One common approach uses fast spinning systems that encourage the slightly heavier molecules to drift one way while the lighter ones drift another. Another approach historically used diffusion through barriers, letting lighter molecules pass a little more easily. You don't need the machinery tonight, only the feeling of the challenge. Separating near twins requires repetition, precision, and energy, because each stage makes only a small improvement, and because the process touches the boundary between civilian fuel cycles and dangerous possibilities, it is also surrounded by strict oversight, safeguards, and international attention. In the calm language of responsibility, enrichment is treated like a capability that must be handled with care. So, when you hear that enrichment is hard, it is not because the physics is mystical. It is hard because it is finicky. It is hard because the difference you are chasing is tiny. And it is hard because the world has agreed that this particular kind of patience should not be casual. Tonight, let that land as a gentle lesson. Sometimes the most powerful technologies are defined not by their brilliance, but by the discipline required to keep them in the right hands, moving at the right pace. In practice, enrichment facilities are built around consistency, monitoring, and accounting, because in this world the numbers must always add up, not only in physics, but in trust, where verification helps the world breathe. It is one of the reasons nuclear energy can feel like a paradox. The same atom that can steady a grid also requires the world to steady itself with rules. With that patient process in mind, we can finally step into the calm architecture of nuclear power. It helps to remember that a nuclear plant is, in many ways, a familiar kind of place. Its purpose is to make heat, and then to use that heat to do what humans have long known how to do: boil water, make steam, turn a turbine, spin a generator, send electricity outward into the waiting grid, where it becomes lights in windows, fans in summer, and quiet chargers beside a bed. The nuclear part is the heat source, tucked inside the plant like a disciplined fire. Fuel is arranged in solid form, designed to stay where it belongs and surrounded by structures meant to keep both heat and radiation within carefully defined boundaries. A coolant carries heat away from the fuel the way water carries warmth away from stones in a riverbed. Sometimes the coolant is water itself. Sometimes another fluid chosen for its stability. But the role is always the same. Carry heat steadily. Never allow it to pile up. That heat is then transferred to a separate water loop or used directly to make steam, depending on the reactor design. And the steam does what steam always does. It expands, it pushes, it turns blades, and those blades turn the rotor of a generator, where magnets and coils trade motion for current. If you have ever watched a ceiling fan spin, you already understand the last step of the chain. What changes is only the source of heat. And because the source is nuclear, the plant is built like a layered shell. Fuel contains the fission products. The reactor vessel contains the fuel. A containment structure surrounds the vessel. Each layer is a quiet promise that boundaries matter. Not because the universe is chaotic, but because humans are wise when we assume that systems deserve redundancy. In some places, the plant's cooling towers release only water vapor, rising as pale clouds that look like breath. It can be oddly peaceful to know that much of the visible motion is just water cycling through heat and sky. Tonight, let the image be simple. A warm core, watched and measured, water moving in loops, steam turning gently, electricity leaving silently. A complicated achievement doing an ordinary job with extraordinary care. Outside the containment, there are control rooms with screens and instruments, people watching trends the way sailors watch weather. They listen for small deviations early because in complex systems, early attention is the gentlest intervention. And when everything is working, the plant's work can be almost boring, which is exactly the point. A safe system is meant to feel uneventful, like a bridge you cross without thinking. Somewhere nearby, transformers quietly raise voltage for transmission, preparing the energy for its long trip across distance. Even that feels like bedtime. Power made portable, sent out like a message into the dark. The most important word in nuclear power is not nuclear. It is control. And control, in the calmest sense, is a set of habits. It is the practice of building systems that do not rely on a single perfect moment. Reactors are designed so the chain reaction can be adjusted, slowed, or stopped, and so the heat can be removed even when surprises happen. Control elements that absorb neutrons can be moved into place to reduce the reaction rate, like shading a lamp until the light becomes softer. In many designs, the physics itself offers a kind of self-correction. As temperature rises, the conditions that favor certain reactions can become less favorable, helping the system resist runaway behavior. This is what engineers mean when they speak of negative feedback, a steadying tendency, like a boat that rights itself after a small wave. Then there is cooling, the quiet hero of the story. Removing heat is the constant work that keeps a reactor in its comfortable range. So plants are built with multiple cooling paths, backup power, emergency procedures, and training routines that repeat until the body remembers them. There are sensors, alarms, checklists, and teams who practice unlikely scenarios the way pilots practice landings, so that calm becomes muscle memory. And around all of this sits the deeper layer of containment, designed for the idea that even if something goes wrong inside, the outside world should remain ordinary. Steel, concrete, seals, and barriers. Not because people expect disaster, but because they respect probability and they respect consequence. This is the heart of what is often called a safety culture. It is not a single device. It is a way of thinking. Assume you can be surprised. Assume you can make mistakes. Build so that mistakes do not become tragedies. Tonight, you can let this chapter feel like an antidote to the word power. Power without discipline is noise. Power with discipline is steadiness. And steadiness is a kind of comfort, especially at night. So, when we speak of nuclear energy, we can also speak of vigilance as a gentle form of care, the way you might check a sleeping child's blanket, not because you expect trouble, but because you love what you are protecting. Safety culture also includes humility. It treats near misses as lessons, encourages reporting, and prefers slow, careful decisions over rushed confidence. At night, that humility can sound like a comfort. It says, we know we are human, so we build in space for correction, and we keep the world outside the walls calm and unchanged. There are also regulators, inspectors, and independent reviews, layers outside the plant that exist to keep standards steady across years and people. In a sense, the system is designed so that no single person has to be heroic. At night, heroism is not what you need. You need quiet competence, routines that hold, and design that lasts. And yet, none of this engineering appeared in a vacuum. It emerged from human needs and human imagination and the long desire to make reliable energy from limited fuel. In the 20th century, cities grew brighter, industry grew louder, and electricity became a kind of second bloodstream, carrying usefulness into homes and hospitals. People sought energy sources that could run day and night, not only when wind was strong or rivers were high. They sought dense fuels that could travel and technologies that could scale. And in the same era, science was learning with almost dizzying speed that the atom was not indivisible at all. There were discoveries about the nucleus, about neutrons, about the possibility that splitting heavy atoms could release heat in astonishing quantities. At first, it was a scientific astonishment, the way a new continent might feel on a map. Then history accelerated, and the same understanding was pulled into the urgency of war. We will hold that part of the story carefully when we reach it. without spectacle, without lingering. For now, it is enough to notice that nuclear technology grew in a world that was both hopeful and afraid, capable of brilliant cooperation and sudden panic. After the war, many people asked a quieter question. Could the atom's energy be used for ordinary good, for electricity, for medicine, for ships and cities, for the practical work of making life safer and more comfortable? That question shaped an entire era of policy, science, and engineering. It shaped how nations talked about safeguards, about transparency, about what should be shared and what should be restrained. It shaped the difference between a controlled reaction that warms water for decades and an uncontrolled release that scars memory. Tonight, we keep our attention on the controlled path. We stay with the image of a disciplined hearth, the patient work of enrichment and fuel preparation, and the steady loops of water and steam. And as we drift forward, we will begin to trace the timeline of the nuclear age, not as a parade of dates, but as a lesson in how quickly knowledge can grow and how slowly wisdom must learn to follow. Let that thought relax you rather than tighten you. Wisdom does follow. Often it arrives as practice, as safeguards, as treaties, as the quiet insistence that some doors should remain heavy. And in the next segment, we'll begin that historical walk, listening for the moments when curiosity became capability and capability asked to be guided. There were also quieter applications that grew alongside power. Radioisotopes became tools in medicine, used in small controlled doses to diagnose and treat, and in science to trace flows and understand processes. So the nuclear age is not only a story of fear. It is also a story of measurement, of care, and of the slow construction of institutions designed to keep the tempo gentle. By the middle of the 20th century, the world had learned a new kind of arithmetic. Not the arithmetic of money or miles, but the arithmetic of the nucleus, where a speck of matter could yield a great deal of heat. Scientists had mapped the atom more clearly, and they had found the neutron, a quiet particle that can slip into a nucleus without being repelled by charge. They learned that some heavy nuclei can split, releasing energy and more neutrons, a pattern that can multiply. In peaceful language, it was a discovery about nature. In the language of an anxious era, it became a discovery about urgency. We will not walk through that urgency in detail tonight. We will only acknowledge gently that knowledge can be pulled toward the fastest use of itself, and that the 20th century offered the most sobering example. For a brief period, the tempo of discovery outran the tempo of wisdom, and the world saw what happens when nuclear energy is released too quickly. Afterward, the question changed. How do we keep this power from racing again? How do we surround it with caution, with rules, with verification, with a shared agreement that some speeds are unacceptable? In the years that followed, many people spoke about turning a frightening discovery toward ordinary work. Research moved into power stations, into ships, into laboratories, that produced isotopes for medicine and industry. The same idea kept returning. If the reaction can be kept steady, it can be kept useful. But usefulness required humility. It required clear lines between civilian goals and military ambition, and the recognition that some materials and processes deserve special scrutiny because they could be misused. So safeguards became a kind of quiet choreography, tracking fuel, verifying declarations, sealing containers, auditing flows, small acts of vigilance that add up to reassurance. They are not perfect, but they are an attempt to give the future fewer reasons to hurry. If that sounds heavy, let it soften. These systems are, in their own way, bedtime things. They are routines meant to keep the world ordinary, so that most nights can remain just nights. And beneath all the policy and paperwork, the physics stays the same. The nucleus offers energy, and the moral work is choosing the tempo. Tonight, let the lesson be simple and calm. The most powerful part of the nuclear age is not the reaction itself. It is the decision to slow it down and to insist that the light we make should never come at the price of darkness elsewhere. Some called it a peaceful atom. Some called it responsible stewardship. But the feeling was the same. Keep the science, slow the danger, and make room for careful cooperation. Even that effort is imperfect, yet it matters, because it keeps attention awake while the rest of the world sleeps. With the history held carefully, we can return to the quieter craft that grew alongside it. Nuclear power, at its best, is an exercise in patience. It takes the chain reaction we discussed earlier and turns it into something almost boring, the way a well-built bridge turns gravity into an unremarkable daily crossing. In a reactor, the fuel is arranged so that the reaction can continue, but only within boundaries. Neutrons are slowed or absorbed, temperatures are monitored, and the system is designed so that small changes tend to push it back toward steady conditions. Engineers speak of margins and redundancy, meaning there is more than one way to keep things safe, more than one path for heat to leave, more than one backup for a backup. This is sometimes called defense in depth, and it is really just a layered kind of kindness, because the nucleus does not care about human schedules, human fatigue, or human pride. So we design as if people can be tired. We design as if a pump can fail. We design as if the unexpected will someday arrive. Over time, countries built plants and connected them to grids, adding another kind of steady heartbeat to modern life. Electricity from nuclear stations does not depend on sunshine or wind, which can make it feel like a reliable lantern through long nights and winter storms. And yet, reliability is earned, not assumed. The nuclear industry learned, sometimes painfully, that small missteps can have large consequences, and that transparency matters as much as machinery. So training became rigorous. Procedures became precise. Reporting near misses became a virtue rather than a shame. The goal was not to appear perfect, but to learn quickly and to build humility into the system. If you have ever improved at anything over time, you understand this instinct. You stop trying to be fearless, and you start trying to be careful. You replace guesswork with checklists. You replace bravado with practice. In many places, regulators sit outside the industry, watching and setting standards, so that the pursuit of profit or speed does not outrun the pursuit of safety. And inside the plants, quiet monitors keep listening, measuring temperature, pressure, flow, and radiation levels, like a room full of attentive clocks. Tonight, let the word nuclear feel less like a sharp edge and more like a discipline of measurement, a discipline of restraint, a discipline of steady, ordinary electricity, produced by a process that asks humans to be their most responsible selves. Public trust is part of the engineering. People want to know what is happening behind the walls, and they deserve clear answers, not slogans. So the story includes communication, oversight, and the slow rebuilding of confidence after moments when confidence was shaken. In this way, nuclear power becomes not only physics and hardware, but a social contract, renewed quietly. And when a reactor has done its quiet work, another chapter begins. Not a dramatic chapter, but a patient one, because nuclear technology always carries time in its pockets. Spent fuel is not used up, the way a log in a fireplace becomes ash. It has changed. Some of its atoms have split, creating new elements called fission products, and some atoms have captured neutrons and become heavier, forming other radioactive materials. These mixtures can remain energetic for a long time, which is why they must be handled with careful cooling, shielding, and secure storage. At first, the concern is heat. Freshly removed fuel still produces warmth from ongoing decay, like a kettle that stays warm even after the flame is turned off. So it is placed where heat can be carried away, in systems designed for steady cooling and constant monitoring. Over longer periods, as the heat fades, the story becomes less about temperature and more about containment. The goal is simple to say and hard to practice. Keep the material isolated from people and ecosystems for as long as needed, because some isotopes settle quickly, and others keep their slow rhythm for decades, centuries, or longer. In this, waste management becomes a conversation with deep time. Engineers speak of barriers, not one barrier, but layers. A solid fuel form, a sealed container, surrounding materials that resist corrosion. And in some plans, the final barrier is geology itself. Stable rock formations chosen because they change slowly and keep water from moving freely. The idea of a deep geological repository can sound strange, like burying a secret. But at its best, it is closer to returning something to the earth with a map and a lock, acknowledging that the earth already knows how to hold long-lived materials. We see this in nature. There are places where radioactive elements have remained trapped in minerals for millions of years, not by luck, but by chemistry and geology. So the ambition is to imitate that calm stability on purpose. None of this is simple, and it is not the same everywhere. Different countries choose different strategies, shaped by politics, geography, and public trust. Some reprocess certain materials, treating what remains as a resource. Others focus on long-term storage, emphasizing isolation and monitoring. But the moral center stays steady. If we benefit from the energy, we also inherit the responsibility. Tonight, let that responsibility feel less like a burden and more like adulthood. It is the quiet willingness to think beyond our own lifetimes, to build systems that outlast us, to treat the future as real and worthy of care. And in that care, the nuclear story begins to sound like a bedtime story again. Slow, layered, and designed to keep the world peaceful while the years pass. To make the time scale feel less alien, it helps to remember that the Earth has been practicing patience longer than we have. In fact, there is a remarkable place where nature itself once ran a kind of nuclear reaction. About 2 billion years ago, in what is now Gabon, uranium, in a deposit called Oklo, reached conditions where fission reactions could occur naturally, moderated by groundwater. It did not become a weapon. It did not become a power plant. It became a quiet geological event, cycling on and off as water moved, leaving behind traces that scientists recognized much later. The story of Oklo is soothing for one reason. It reminds us that fission is not an invention. It is a behavior of matter, and the planet has held its consequences within rock across immense time. That does not remove our responsibility, but it does offer perspective. The Earth is capable of containment when conditions are right. So, our task is to choose conditions that are right and to be honest about what we are asking the future to hold. This is where governance returns, not as politics, but as a kind of shared bedtime agreement. Because the same knowledge that can produce electricity can also be misused. So the world has built systems of safeguards, inspections, and accounting meant to discourage diversion and to encourage transparency. These systems are imperfect, but they are a form of collective self-control. They say, we will keep watching. We will keep counting. We will keep asking for proof, not because we are cynical, but because we know the stakes. In calmer words, it is the idea that trust should be supported by verification. And this is also why enrichment and fuel cycles are treated with such care. Not because the science is forbidden, but because the capability is sensitive. So there are treaties, export controls, monitoring regimes, and international agencies whose work is mostly paperwork, but whose purpose is peace. A quiet kind of peace, built from ledgers and seals and routines. It can feel strange to imagine peace built this way, but many parts of modern life rely on the same idea. Bridges are safe because of inspections, Airplanes are safe because of maintenance schedules. Medicine is safe because of testing and labeling. In each case, the calm result depends on relentless attention behind the scenes. Tonight, let that be the mood. A world that has learned slowly to put rails around its own speed. A world still learning, still imperfect, but willing to keep the watch. And as we approach the end of our journey, we can begin to gather the threads, stardust and stone, heat and steam, light in windows, history's shadow held at a distance, and the steady lesson that power becomes livable only when it is guided, measured, and kept slow. And now, as the episode quiets, we return to where we began. Not to a headline, not to a diagram, but to the feeling of the earth beneath you, immense and unhurried. Uranium is, in the end, a piece of the universe's oldest work. It was made in rare cosmic moments, scattered into dust, gathered into a planet, and tucked into minerals that waited through ages of rain and silence. For most of its existence, it did nothing dramatic. It simply decayed at its own slow tempo, warming rock by tiny degrees, leaving faint traces that no one could hear. Then humans arrived, with lamps and questions, with instruments sensitive enough to notice the invisible. We learned that the nucleus can store extraordinary energy, and that the same physics can be invited into a steady hearth or forced into a terrible rush. That duality can feel heavy, so tonight we let it become a lesson instead of a weight. The lesson is not that nature is dangerous. The lesson is that nature is powerful, and that the gentlest thing we can add to power is restraint. In the peaceful uses of uranium, restraint looks like engineering. It looks like layers and redundancy, like careful training, like habits that do not depend on heroism. It looks like monitors that listen all night, like a quiet nurse checking a patient's pulse, not because something is wrong, but because attention is love. In the darker chapter of history, restraint looks like treaties, safeguards, and the long, imperfect work of keeping certain tempos from returning. It looks like people choosing to slow down even when they could hurry. And in the waste chapter, restraint looks like patience across generations. It looks like containers designed to last, repositories designed to stay dry and still, and records left behind like gentle warnings, so the future can remain ordinary. If there is a comfort here, it is that wisdom can grow. Often it grows after we are humbled. Often it grows in the quiet work no one celebrates. And for you, tonight, the takeaway can be simple. You do not have to carry the world's power on your shoulders. You only have to carry your own small choices with care. A kind word instead of a sharp one. Fairness instead of impatience. A slower breath, a steadier pace. Because restraint is not only a policy for nations, it is also a practice for a single human heart. So, as you settle deeper into the night, imagine the earth holding its minerals, the grid carrying its invisible currents, and the world learning, slowly, imperfectly, to keep the tempo gentle. Let your thoughts become quieter. Let your body become heavy in the softest way. And let the story fade back into stone and starlight where it began. And the world slows, and so do we. Good night.